Hey students, welcome to your first actual honors vodcast. This is the first time that we're really covering a topic that the other class is not covering. This is part of Unit 2, so part of our matter unit, and it will be on the test on Tuesday. But we're going to cover activation, energy, and catalyst. It's a pretty short little video, and there's not like a bunch of math or anything in it, but make sure that you understand the graphs in particular, and then you can go back to get any of the notes that you need to as we go through. So, first off, we're going to start off with the law of conservation of energy, and this is a law that you probably heard for the first time back in 3rd or 4th grade science in elementary school. Basically, it just means that energy can't be created or destroyed, and that's in an ordinary chemical reaction. We'll talk later about nuclear reactions, but in general, we can't create or destroy energy. We can turn it from one form to another, but we can't create or destroy it. Now, if we can convert it from one form to another, one of the biggest things that we do is it gets converted to heat. And heat has a really important definition here. Heat is a transfer of energy. Okay, so you've got something cold and something hot, and the heat then is going to flow from the hot object into the cold object. Okay, so like you've got a can of Coke in your hand. Just by virtue of you holding that can of Coke, it's going to get warmer because energy is going to flow from your hand to the Coke. And so for heat to happen, there has to be movement of energy, okay, transfer of energy in some way. Remember from our last stuff that we talked a little bit about exo and endothermic. Well, to know really if something's exo or endothermic, we have to know basically what the system is and what the surroundings are. So there's a picture here. You don't necessarily have to draw the picture, although it might be a good idea. But these definitions are pretty important. So the system basically is what you're looking at, okay, like the part that you're observing. So like if we're doing a reaction, okay, the stuff that's inside of the flask is the system, okay, and then everything but the chemicals inside of the flask are the surroundings. Now, why this is important for us is because this then determines whether energy is going into the system or out of the system. So like if you're doing this reaction and we look back at like the reaction that on the video that I did a couple weeks ago where I dropped the zinc down into the acid and it bubbled up and I showed you that the flask was really hot, that's an exothermic reaction. It made the flask hot. The surroundings got hot. So in that case, the energy was moving from the system to the surroundings. Okay, that's exothermic. Endothermic means energy is moving from the surroundings into the system. So like if you take a can of Coke out of the fridge and you set it on the counter, the heat from around the can of Coke from the room temperature is then going to start to heat up the Coke. So that's going to be endothermic. It's going to be pulling energy in. Okay, so that goes to the two definitions that we are just talking about, exo and endo. Exo means goes out of the system to the surroundings. Endo means that it goes from the surroundings to the system. Okay, so you should have those definitions down from one of the previous vodcasts, but just make sure you know this. Remember again that if it is an exothermic reaction, then it's going to have a negative sign. And if it's an endothermic reaction, it's going to have a positive sign. When we calculate delta E or Q in the calorimetry equation that we've been calculating, negative sign means exo, positive sign means endo. Okay, that leads us to a pretty important law, and this law is called the first law of thermodynamics. Basically, it is a sort of a restating of the law of conservation of energy. It says that the energy of the universe is constant. So if you look at this formula up here, and don't worry, you're not going to have to calculate anything really with this formula, but what it means is the energy of the universe never changes, and the energy of the universe is made up of the system plus the surroundings. So what this means is that if the system loses energy, the surroundings are gaining energy, and vice versa. So if the surroundings lose energy, the system has to pick up energy. Okay, that makes pretty good sense. I mean, if the reaction is giving off energy, it's making the beaker hot. So the chemicals are losing energy, but the beaker and the surroundings are gaining energy. Okay, the energy throughout the whole universe is always constant. It gets moved from place to place. It gets its form transferred, but it's constant. Okay, so real quick, we want to talk a little bit about collision theory. This is like our only real foray into the idea of chemical kinetics. Remember, kinetics means that things are in motion. And when we talk about chemical kinetics, remember we're going back to kinetic theory, the idea that molecules are always moving around. And so the idea of collision theory is basically just what it sounds like. The idea is that molecules have to collide in order to react. And so really quickly here, let me show you just a short little animation here. And what we're going to do here is I'm just going to have two reactants, A and B, Okay, they're different colors, and you can see them here. So A and B, same numbers of each of them. When they collide, they make P, which are going to be the red ones. And if you watch this, what you'll notice is they have to run into each other for that to happen. Okay, the higher the temperature, the faster this happens. So right now we're running at a temperature of like 100. Okay, so if we then change that and say we ran it at 10, okay, it's going to take a lot longer. They're not going to, and what you'll notice is they're running into each other, but they're not reacting. Okay, so what's the difference? Okay, the difference is they don't have enough energy to react. Okay, if we crank up the temperature a little bit, okay, then they start to react. Okay, so let's go back to our notes. So what does that have to do with anything? Well, here's the idea. Molecules have to collide to react, and they have to have a certain amount of energy. They have to be moving at a certain rate of speed for that reaction to happen. Okay, and that amount of energy is called the activation energy, and it's all related to this diagram. So you need to copy this diagram down. If you're picking one to copy, I guess copy the one on the left is probably a little bit easier to understand. Has all the stuff that we need. Right here, okay, this little the red line right here, that is the E sub A. That's what that says there, E with a little subscript A, and that means that's the activation energy. That's how much energy they have to have in order to react. And so you've got reactants over here, and if they have enough energy, they basically can make it to the top of the hill. At the top of the hill, they form what's called a transition state or an intermediate, and then they can come down the hill to form the products, the end result. Okay, so this graph is super important. Being able to identify everything is important. So you've got reactants, you've got transition state, products, activation energy. Okay, a little bit easier to see here on this one. These are probably a little bit clearer. So activation energy is basically how high the hill is. Okay, you got a baseline that you start with, top of the hill, measure the distance between them. That's your activation energy. Okay, at the top of the hill is your transition state or your activated complex, your intermediate. Could be called any of those things. Basically, that's like the middle point. Okay, so like if you were baking a cake and you pulled it out of the oven halfway through, that would be this transition state. Okay, and then we get down to the reactants and the products. Okay, now if you note this definition off to the side here, it says that it's exothermic if the products end up lower than the reactants. So the reactants start here, and we drew our little baseline here. Okay, if the products are lower than that, then that is exothermic, because what that's going to give us is, if you see right here, there's delta E. Okay, delta E means that we've calculated that from calorimetry. If delta E is negative, in other words, we started here and we went lower, okay, so negative, then that's exothermic. It's endothermic if you end up higher than you started. So like on this graph, we started here, our products are higher than that, so that would give us a positive delta E, and so that is going to be an endothermic reaction. Okay, one last thing here. A catalyst, what a catalyst does, and you guys heard about catalysts in biology, you called them enzymes, you said that they were biological catalysts. And the definition of catalyst that we usually get is up here. It's a substance that speeds up a reaction without being consumed itself. But what that really means for us in terms of collision theory and in terms of kinetics is that a catalyst lowers the hill. Okay? So if from here, if from here to here is the activation energy, okay, with the catalyst, the blue line is the catalyzed pathway, the hill is much smaller. So what does that mean? That means that more molecules can react because they need a lower energy. The threshold energy to react is much lower. So like if we look back at that beginning thing where everything was bumping into each other, they could bump into each other at a slower speed and still be able to react with the catalyst. And some of the catalysts almost completely flatten the line out. Okay, so like you might all of a sudden see the line doing something like, it would start here and then it would just barely go up at all and then come down. Okay, some catalysts work that way. So sometimes they lower it a little, sometimes they lower it a lot, but the idea is that they make the hill smaller. Okay, that was a lot of information packed in a really short vodcast, guys. But make sure that you get those graphs, know where the parts are, okay, and know the simple definitions. And here's what you're going to definitely want to make sure that you know. You want to be able to look at a graph and tell if it's exo or endothermic. You want to be able to identify the activation energy, reactants, products, transition state, and you want to be able to draw what a catalyst would do. And that's pretty simple. You just make the hill shorter. Okay? All right, guys, thanks a lot.